This talk is about differentiation and integration, the two branches of calculus. So what is calculus, and what are differentiation and integration? What were the contributions of Newton and Leibniz? And what is the fundamental theorem of calculus? Differentiation is concerned with how fast things move, change or grow, such as the varying speed of a moving object. Mathematically, it involves finding the slopes of tangents to a given curve. For example, in the picture on the right, showing the graph of y equals x squared, what is the slope of the slanted dotted line at the point where x is 2 and y is 4? Integration is concerned with the areas of shapes in two-dimensional space, or of volumes in three-dimensional space, though that won't concern us today. For example, on the right, showing the straight line graph of y equals 2x, what's the area of the shaded region extending up to x equals 2? So those are differentiation and integration. They sound very different, but might there be a connection between them? Here's a simple example that illustrates both processes. Suppose that we're travelling along a road at a constant speed of 60 kilometers per hour. After 4 hours, the distance we've travelled is 240 kilometers. And after x hours, it's 60 times x kilometers. On the right is the distance time graph y equals 60x, showing the distances y that we've travelled after periods x of time. Here the slope, or distance over time, that is the speed, is everywhere 60. Below is the corresponding speed time graph y equals 60, showing the speed at any time x. Here the area under this graph is the speed times the time, which is the distance travelled. After 4 hours, it's 240 kilometers as shown, and after x hours, it's 60x. Suppose now that our speed increases with time, so that our distance time graph becomes gradually steeper. At any moment, our instantaneous speed is the steepness of the curve there. That is, the slope of the tangent of the graph at that point. And to find this instantaneous speed, we'll take a short interval of time and calculate the average speed over this interval. We'll then let the interval become arbitrarily short. Here's an example involving the graph of y equals x squared, where we wish to find the slope of the tangent to the graph at the point A, where x equals 4. To do so, we'll take a nearby point B with x value 4 plus h, where h is small. Then the average speed over this short time interval from 4 to 4 plus h is the slope of the diagonal line AB joining these 2 points. This slope being the difference in their y values divided by the difference in their x values, sometimes called rise over run. This is 4 plus h all squared minus 4 squared, all divided by h. Multiplying out the bracket, we get 16 plus 8h plus h squared minus 16 all over h. And cancelling the 16s gives 8h plus h squared over h, which is just 8 plus h. But this only approximates the slope of the tangent at A. To find the required slope, we now let the point B approach the point A. That is, we shrink h to 0. The slope of 8 plus h then becomes 8, so that 8 is the instantaneous speed at A. To find the slope at a general point on this curve, our calculations are similar. Here on the left for reference are the calculations we've just seen for x equals 4, and on the right is the general case. Here, to find the instantaneous speed at any time x, we let A be the point on the curve at time x, and let b be the point at time x plus h, where h is small. Then the slope of AB is x plus h all squared minus x squared all divided by h. Multiplying out the bracket as before, we get x squared plus 2hx plus h squared minus x squared all divided by h. The x squared terms then cancel, leaving 2hx plus h squared divided by h, which is 2x plus h. So when we shrink h to 0 as before, the slope becomes 2x, which is the instantaneous speed at a for any value of x. Isaac Newton's approach to finding slopes was similar in idea, but with different notation. In his studies on curves, his main interest was in velocities and other variables that change with time. In particular, he thought of x and y as flowing quantities, or fluents, and the rates of change in x and y as fluxions. On the left is the frontispiece of his book on differentiation, The Method of Fluxions, where the marksman in the centre is aiming at a bird in motion. Here, for the curve y equals x squared, he would find the slope, or instantaneous speed, at any point A with coordinates xy by taking a nearby point B with coordinates x plus PO, y plus QO. Here O, like h earlier, is small, and P and Q indicate speeds in the x direction and y direction. So the slope of the line AB is QO over PO, which is Q over P. But the point B lies on the curve. So y plus QO is the square of x plus PO, which is x squared plus 2xPO plus P squared O squared. Also, y equals x squared everywhere, so we can cancel these, leaving QO equals 2xPO plus P squared O squared. Dividing by O and by P then gives us Q over P equals 2x plus O as the average speed over AB. Finally, ignoring the small o term gives us the instantaneous speed 2x as before. But although these methods generally worked well in practice, they raised logical difficulties. In particular, dividing by h or by o meant that they cannot be zero. But at the end, we let both of them be zero. The whole subject thus had shaky foundations, which were not fully resolved until the 19th century with the use of limiting processes. But that's another story. Meanwhile, in Germany, Gottfried Leibniz was taking a different approach. He was not interested in flowing quantities, but dealt directly with the curves themselves. In the autumn of 1675, he introduced the infinitely small differentials dx and dy, which measured small changes in x and y, and corresponded to Newton's PO and QO. He then derived his rules for differentiation, which enabled him to carry out calculations. His first rule says that if A is a constant, then d of A is 0, and that the differential of AX is just A times the differential of x. The second rule says that d of x plus y is the same as d of x plus d of y, and similarly for subtraction. The third one then gives the differential of a product x times v, and the fourth gives the differential of a quotient v over y. Let's see how these work in practice. To find the differential of x squared, we use rule 3 with v equals x, giving d of x times x equals x dx plus x dx, which is 2x dx. Then to find the differential of x cubed, we use rule 3 again with v equals x squared. Here we split it as x times x squared, giving d of x times x squared equals x squared dx plus x d of x squared. But d of x squared is 2x dx, as we've just seen. And we get d of x cubed is 3x squared dx. We can also deal with sums and multiples. To find d of 4x cubed plus 5x squared, for example, we use rules 1 and 2 to split it into 4 times d of x cubed plus 5 times d of x squared, which is then 4 times 3x squared dx plus 5 times 2x dx, or 12x squared plus 10x dx. For the slope, he then divided by dx to give dy over dx, or dy by dx. For example, when y is x squared, the slope dy by dx is 2x. And when y is x cubed, dy by dx is 3x squared. More generally, if y equals x to the n, then dy by dx is n times x to the n minus 1. There's also another way of writing this. If y is a function f of x, then for the slope dy by dx, we sometimes write y dash or f dash of x. Let's now turn our attention to integration, the finding of areas. If y equals 2x, then the area up to the point where x equals 4 and y equals 8 is the area of the triangle shown, which is 1/2 times the base times the height, which is 16. And more generally, the area up to the point x is 1/2 times x times 2x, which is x squared. For more general curves, where we cannot so easily calculate the area, we can approximate it by drawing rectangles below the curve, calculating their areas and adding them up to give the total area. Obviously, the more rectangles there are, the better this approximation will be. This was essentially the approach of Leibniz, who took infinitely thin rectangles, that is lines, and regarded the area as the sum of all these lines. As he said, using the Latin word omnia, meaning all, let omnia L be the sum of all these lines. He then said, it will be useful to write the sign shown here, called an integral sign, for omnia, so that the integral of L equals omnia L, the sum of all the L's. This symbol, representing an extended capital S, was an abbreviation for summa, meaning sum, and here, on his manuscript, is its very first appearance in the year 1675. Newton, on the other hand, didn't sum lines to find areas. Instead, he produced rules for finding them. One such rule was that if ABD is the area under the curve shown on the right, and if the curve is y equals a times x to the power m over n, then this area is na over m plus n times x to the power m plus n over n. He then gave some examples, such as if y equals x squared, which is 1 times x to the 2 over 1, then a and n are both 1 and m is 2, and we get 1/3 times x cubed. And if y equals 4 times the square root of x, or 4x to the 1/2, then the area is 8 over 3 times x to the 3 over 2, or 8 over 3 times the square root of x cubed. In Leibniz's notation, we now write these areas as the integral of x squared dx equals 1/3 x cubed, and the integral of 4x to the 1/2 dx is 8/3 times x to the 3/2. So how did Newton find areas? To find the integral of 4x to the 1/2, he would guess the answer to be y equals 8/3 x to the 3/2, and then check by differentiation that the slope is indeed 4 times x to the 1/2. So although differentiation and integration had always appeared to be completely different types of operation, they now seemed in some sense to be inverses of each other. This had been suspected by a few people in the 17th century, but the credit for explaining why this is the case is due to Newton and Leibniz. This inverse relationship between finding tangents and calculating areas is now known as the fundamental theorem of calculus. We differentiate to find tangents, and we integrate to find areas. And if we do either of these, and then follow it by the other, then we get back to where we started. We can write this formally in symbols. Let y be a function f of x. If we now differentiate to get f dash of x, and then integrate the result, we get back to f of x. And the other way around. If we find the integral of f of x, and then differentiate the result, we get back to f of x. But although Newton and Leibniz should both receive the credit for this, their methods were very different. For differentiation, Newton studied fluxions that change with time, whereas Leibniz worked directly with the infinitely small differences between successive values on curves. And for integration, Leibniz worked directly by developing methods for summing lines, while Newton often guessed the answer and checked it by differentiation using the fundamental theorem. Today, we mainly use Leibniz's notation of dy by dx for differentiation and the integral sign for integration, two notations that he introduced 350 years ago, remarkably within just 3 weeks of each other. So who got there first? It was probably Newton in the 1660s who first explained this inverse relationship between the calculations of tangents and areas. But although he circulated his results privately to friends, he didn't publish them until much later. Leibniz was the first to publish in the 1680s. Unfortunately, this led to a bitter priority dispute, with Newton's supporters accusing Leibniz of plagiarism. The Royal Society of London set up a commission to investigate the matter, and this ruled in favour of Newton. But this was not Newton's finest hour. As president of the Society, he had personally selected the members of the commission and written much of the evidence for it to consider. Leibniz was devastated by the result and died shortly afterwards. And with that sad ending, I thank you for listening.